Okay, the L'Hopital rule. The L'Hopital rule is probably one of those rules which you'll find really, really easy. And this particular rule is actually here to make our life easier. Each and every rule, to be honest, is created, has been created to make our life easier. Um, but this particular rule, I'm telling you, you'll like it. You'll definitely like it. Uh, but uh, obviously, there is um, a problem using this rule as well. One problem I have seen from my previous experience is that overusing this rule. I'll come back to it. When I start doing it, I'll explain what did I mean when I said uh, overdoing it. Okay, so let's first see the statement, and hopefully we'll see lots of examples of it. Okay, so the L'Hopital rule says you have, let's say you have two differentiable functions, okay, on an open interval. And the first derivative of the second function, let's say g, is non-zero when the value is when you are evaluating rather at a non-zero value. Okay. Now, what does this mean? So let's say you have a function. You are trying to evaluate the derivative at a point which is not zero, which could be anything, but it's not zero. And we're trying to say that this derivative, if we evaluated it at that non-zero value, this derivative will be non-zero as well. Now, the the limit uh, extends to a for the first function, the limit extends to a for the second function. If both of these are equal to zero, then our theorem says, as you can see, the quotient of these two functions when limit extends to zero will be equal to the quotient of the derivatives of those when x tends to zero. Okay, I know again there are so many letters, there are so many notations here, so these definitions or statements often doesn't make sense. But when you start doing problems, um, it will make more and more sense. Okay. All right. So this is the statement. Obviously, you need to know it, but you don't need to memorize it. Okay. Whenever you use it, you just have a side note that hey, on this line, I'm using the L'Hopital rule. Okay. All right. So I think I should show one example and then I'll come back to it. Okay. Uh, okay, let me show it from this graph, and then I'll come back to the definition statement again. So I'm going to share the screen of my iPad. So I want you guys to have this slide open so that you can actually cross-check what I'm trying to do here on my iPad. Okay. So let me start sharing the screen. I wish I could share both screens. So is there anyone who knows uh, if it's actually possible to share two screens simultaneously? Anyone? I haven't seen this, but it could be a possibility. I don't know. Is it possible?
Do it on a computer. I think you can do it.
Are you sure?
Yeah.
Okay. Then I think I can give it a try.
Like you can like split screen it.
Okay, let me see whether I can actually do it. No, it doesn't work. Maybe I'll have to see this. I'll have to check. I don't think it's the right time to do that. So yeah. Anyway, I think you guys have this slide. So let's just keep doing it for today at least. If I can figure this out, that'd be nice. All right. Can you see the screen I'm sharing? Is it still the screen of my desktop, or is it?
Yeah, it's still a desktop.
Okay, let me see. All right. Okay, now here we go. I think now it will show my iPad. No, it's not. Ah, gosh, I hate this. Let's see. What happened? Now can you see the screen of my iPad? Yeah, I think so. Yeah, I think it's working now. Right? Can anyone confirm? Okay, perfect. All right. So we are back, and it's 06:24, I believe. 21. Okay. All right. So the statement is trying to say that whenever you have a differentiable function f, oops, and g, you have two differentiable functions on an interval, let's say that's I, and it contains a non-zero point. It contains a point A, first of all, and let's say it's non-zero. So it's saying that your derivative at that non-zero point will be non-zero for the second function, because and I think it should make sense. Sorry. I think it's like that, right? Oh no, it's actually not A. Sorry about that. Okay, and actually it should make sense, and you might be wondering why. So when I'm writing like this, forget about the value of the other things. You can see I'm writing it in the denominator. So if you're trying to use this statement, use this theorem, I'd say, you can clearly imagine this denominator has to be non-zero, right? This statement has to be non-zero. Your denominator can't be zero, because it will be then it will be undefined. It won't help the cause either, anyway. So this has to be non-zero anyway. Okay. All right. So now what they're trying to say that x tends to a, the quotient of these two derivatives, these two functions, will be equal to the quotient of the derivatives. Isn't it funny? And let me show you how. So let's try one example. Let's say x tends to 0, okay? I think the non-zero term is not really needed here. Yeah, we can just say when x is not equal to a. So a could be any value, yeah. All right, so let's say sine x over, what should I take here? Sine x, let's take this one. X cubed, and let's say we have, well, 0, right? So I think we could pick, or let's do it this way. Yeah, let's do it this way, okay? So if I plug in 0, it becomes 0, right? So I can't really plug in the value to get the limit. So what I can do, I can use the L'Hopital rule to avoid this situation. And what the L'Hopital rule is saying here is the functional, the quotient of these two functions is equal to the quotient of the derivatives of those two functions. So that means I can use the L'Hopital rule and write it this way. What's the derivative of e to the x? Anyone? That should be pretty straightforward.
E to the x.
E to the x. What's the derivative of x?
1.
1. So I can use this L'Hopital rule and say that they are equal. See? How does this make my life easy? It's one of those amazing rules which we'll use to you know, unsophisticate our life, I would say. Okay, so now if we plug in x to the 0, we'll actually get a defined value. Can you see that? Because I can now plug in e to the 0, which is 1, and that's the defined value. But when we started, you could see it was actually an undefined one. If we tried to plug it back to the place of x. And if you remember, when we actually calculated these limits, if you remember, I did say that, I think I mentioned this rule, right? This L'Hopital rule. I think someone asked that if there is any way that we can modify it. And I did say that, yeah, obviously we can reduce it by factorization and all that. And we can use the L'Hopital rule in some cases. And this is the rule. This is the rule. I wonder why they have put it here. I think this should have been in the section where we calculated the limit. I'm not sure why they have put it here. Anyway, so this is the use of the L'Hopital rule, as you can see. I can find the first derivative, and I can say still they are equal to each other. Okay. So what I can do is to generalize things right now. Okay. I'll tell you some scenarios where we can use this, where we can use this theorem. Okay. So first of all, we'll use this when we can't really determine the value. So how does the format look like? A format might look like could be infinity over infinity, right? That means when you plug in the value, both the functions could tend to infinity. So it's infinity over infinity. That's an indeterminate form, right? It could be 0 over 0, right? It could be 1 to the power infinity. It could be 0 to the power 0. It could be infinity to the power 0. Okay. If we have this type of scenarios, we can actually use the L'Hopital rule, and it will take care of these scenarios, and you'll see that we can use this to get a defined value. Okay, we can actually get a defined value if we can successfully use the L'Hopital rule. Okay, now I think I should show you more examples. I'll try to show at least one from each. So let me see if we can generate that. But before that, any question from whatever we have discussed so far? We haven't discussed too many, just a statement and how to use it. So any question from it? If you have any question, please let me know, okay? All right, so let me take one example each. Okay. All right, so I don't want to make our, I would say, make up a problem which doesn't look good. So let me use some worked out problems. Okay. All right, so let's try this one. Let's try this one. X unit X tends to 0. Okay. To sine x minus sine 2x over x minus sine x. Okay, let's try this one. I think this would be a very good example. Okay, first of all, let's see if we plug in 0, what happens. Okay, if we plug in 0, sine 0 is 0, sine 2 times 0 is still sine 0, which is 0, x is 0, and sine 0 is 0. So it's actually 0 over 0 scenario. Do you agree? Do you agree when I say this? Just don't
So,
yeah.
so is our answer just undefined then?
No. We'll actually use the L'Hopital rule.
Okay.
Yeah. So since this is 0 over 0, we'll actually use L'Hopital rule to see if we can generate a defined value. Okay. All right. As I said, if any of this scenario arises, we'll use the L'Hopital rule. So what's the L'Hopital rule says? The L'Hopital rule says, oops, sorry, it should be 0. If you find the derivative of each of this term and replace it here, that will still be equal to this. That means the derivative of these terms, of these functions, I should say, this is one function and this is another function. The derivatives of this will be equal to this when x tends to 0, since we have 0 over 0 scenario. Let us slowly go there. So what's the derivative of 2 sine x? Anyone? The derivative of 2 sine x?
Isn't it 2 cosine x?
Very good. So for 2 sine x, it will be, okay, let me use the same color without the arrows. It will make it clumsy. So 2 cosine x, right? 2 is a constant, so it doesn't really harm us. For sine x, we know the derivative is cosine x, so it's 2 cosine x. Okay, minus, what about sine 2x? Anyone? Sine 2x?
Two cosine 2x.
How do you do that?
Chain rule.
Very good. So we know that for a sine function, we expect cosine function as the derivative, right? So if we have sine 2x, in return, we should have cosine 2x. But the formula is actually for a sine x. It's not exactly x, right? So that means we need to use a chain rule, or in other words, we need to have the derivative of 2x multiplied to it. And the derivative of 2x is definitely 2, right? So it's 2 cosine 2x. Do you agree? I'm just using the chain rule. So for this one, it will be 2 cosine 2x. Any question from the derivative part of this? Any question? Excuse me. No questions at all? It's just a simple derivative, right? We're not really doing anything else here. Okay, let's keep doing it. What's the derivative of x? It's 1, right? The derivative of x is always 1. And minus, again, for sine x, we know the derivative is cosine x. So you can write cosine x here. Okay, the L'Hopital rule says this will be equal to each other. Okay, the derivative of that function when x tends to a certain value is equal to the function itself. I mean the quotient of the function, of course. Okay. All right. Now we'll keep doing it until we get rid of this. Okay. So now the next thing is to do is to check if we plug in this value in place of x, whether we have one of these indeterminate form or not. Okay, so let's see if we plug that in, what happens. So now if we plug in 0 in place of x, this cosine x will be 1. This cosine 2x will be 1, will be 2, sorry, because cosine x will be 1, cosine 0 is 1, right? So it will be 2. Cosine, here also you'll have a cosine 0, which will be 1. So this will be 2 as well. So 2 minus 2, it will be 0 in the numerator. And this cosine 0 will also become 1. So 1 minus 1, it's still 0 over 0. We haven't really got rid of that indeterminate form as yet. I'm just checking if we plug in x equals 0, what happens. I'm just checking it, okay? When we started, this was the problem I was given, right? When we started, we saw that if we plug in x equals 0, this quotient will give us 0 over 0, which we don't really want. So we have used the L'Hopital rule once, and we can see that even after using this L'Hopital rule, if we plug in x equals 0, still we have 0 over 0 format. So what does it mean? It means we can use the L'Hopital rule one more time and see if we can get rid of this situation. We can actually keep doing it until it's actually doable. That means there is a place where we have to stop, and I'll show you when. Okay, let me write the next line, then I'll give you a chance to ask questions. Okay, so now what's the derivative of 2 cosine x? The derivative of 2 cosine x? Anyone? Normal derivatives, nothing else. Give it a try.
Is it negative 2 sine x?
Very good, negative 2 sine x, because we know the derivative of cosine x is negative sine x, and because of these 2 in front, it will be negative 2 sine x. Very good. Okay, let's keep doing it. What's the derivative of 2 cosine 2x?
Negative 4 sine 2x.
Okay, yeah, right. Yeah, so the derivative of it is negative 4 cosine sine 2x, but using this negative as well, I think, okay, let me show it one by one. So
It would go to positive then.
yeah, I understand. Yeah, I got it, because when you say negative to start with, I could understand it's the derivative itself. So yeah, using the chain rule again, the derivative of cosine 2x is 2 sine 2x, right? Negative 2 sine 2x. So negative, we'll have 2 in front and another 2 for the derivative of cosine 2x, right? Any question from the derivative part? Oh, sorry, I think, sorry about that. I should use the same color so that you can locate the changes. Okay, so this is the derivative of cosine 2x. Okay, just follow the same color. So for cosine 2x, the derivative using the chain rule is negative 2 sine 2x. Any question from the derivative part again? Because if you do the derivative part wrong, then you will not reach the result you're looking for, right? So it's really important to have the basics right. Okay. All right. What's the derivative of 1? Real quick. It shouldn't take more than 1 second. The derivative of 1.
0.
0. Yep, it's a constant, right? And the derivative of cosine x is, of course, we know this, that it's negative sine x. Okay, so if I now make the adjustments, yeah, I think I should write it in the next line. Okay, although you can actually do it on the same line, but I want to do it so that you can see this will be plus 4 sine 2x. This will be a plus sine x, right? Okay. Now we want to see if we plug in x equals 0, if we have got rid of that 0 over 0 scenario or not, right? We want to check that. Okay. And now if we plug in x equals 0, this will be 0 because sine 0 is 0, right? This will be also 0 because this will be sine 0. And this will be 0 as well because this is sine 0. So we still have 0 over 0. Even after using the L'Hopital rule twice, you can see we have not got rid of the indeterminate form. So we can still use it one more time at least, if not more. Okay, let's try that. So if we use the L'Hopital rule again, that means we'll find derivatives of each of this term one by one and replace it in place of its respective place. Okay. So the derivative of negative sine 2x. Anyone? The derivative of negative sine 2x. No one at all? We're just trying to find the first derivative of this. Forget about anything else. Just imagine this function negative sine 2x, and what would be the derivative of it? Who wants to give it a try?
Don't you just like replace it with cosine because it's like a trigonomic identity?
So what would be the final answer?
It would just be like -2 cosine x.
Exactly, yeah.
Oh,
So first of all, this -2 is not doing any harm to us. And we know the derivative of sine x is cosine x. So that's it, -2 cosine x. Yep. Because that constant will be kept outside using the constant function rule, if you remember. So all we need to care about is the derivative of sine x, which is cosine x, we know that. Yeah, very good. So the next one is 4 sine 2x. Now what should you do? Again, I'm telling you, you need to do this basic derivatives right. Otherwise, this L'Hopital rule won't take you anywhere. Okay, it will not take you anywhere. You'll still, you'll be in the loophole, and you won't be able to come out of it. So obviously, you need to check whether your first derivative, when you are doing it, is right or not. You need to be very careful about it. Okay. So what's the derivative of 4 sine 2x? The algebra here is pretty simple. You just plug in x equals 0 and see whether you have one of these indeterminate form or not. If you have, you can just use the L'Hopital rule. In other words, you can just find the first derivative of each of those terms and replace those in its respective places. That's it. The algebra is pretty simple. But if there is anything complicated here, I don't think anything is complicated here though, but if there is any, that could be the derivative itself. If you somehow make a mistake to find the derivative, then you might be struggling to get your desired result. Excuse me. Okay, the derivative of 4 sine 2x.
Would it be 8 cosine 2x?
8 cosine 2x, yeah, you're right. So obviously the 4 won't really create any problem. For sine 2x, we know the derivative of sine x is cosine x. And of course, this is not exactly x. So the derivative of 2x will be multiplied. The derivative of 2x is 2. So it will be 4 times 2, 8 cosine 2x. So this would be 8 cosine 2x. Any question from this? Anyone? If you are wondering how am I getting this, please let me know. Don't move forward without understanding this this part. I mean, how do I get 8 cosine 2x from 4 sine 2x? Okay, obviously it's the derivative, but how to actually get it? Don't really trust me, okay? You need to reach this when you do it. If you have any doubts, well, you shouldn't move forward. We should, excuse me, we should clarify this first, okay? All right, and of course, the easier one is the derivative of sine x. And there is a straightforward formula for it. It's cosine x. Excuse me. Now, the next thing is we need to check whether or not we have one of these indeterminate forms still, right? So if we plug in 0 here, this will be cosine 0, which is 1. So we'll have a -2. This will be cosine 0, so it will be 1. So 8 times 1 will be +8, which is +6 in the numerator. That's the good news. Finally, we have something, some value, some non-zero value in the numerator. And this is cosine 0, which is 1. So in the denominator, we also have a non-zero value. Whenever we have this, have this format, which is a defined value, which we can determine, we have to stop. We can't use the L'Hopital rule once more. We can't use the L'Hopital rule anymore if we have this format where we have a defined value, where we can determine the value. Okay. So now we'll just plug in x equals 0 and get our desired result, which is 6. That's it. That's our answer. So you can see, let me show the problem all together. Yeah, there you go. If you can see, when we started, it looked like we have an indeterminate form. We have an undefined format, right? We can't really determine this. But after using the L'Hopital rule 3 times, we can see we have finally and thankfully we have a very good result. But we have used it only because we had these indeterminate forms even after using it twice. So that's why we have used it 3 times. And obviously when we have this defined value, we have to stop. We can't use the L'Hopital rule anymore. Any question from this? Take your time, okay? This is really interesting. And I think this is one of those really easier tasks from the derivative part. But you need to make sure that you're using it properly. Any question? No question at all? Okay, so if you remember, I started by saying this, that often students overdo this, overuse it. Now, what did I mean? I meant if you don't stop here, that means uh, if you since you have a defined value, even after getting this defined value, if you keep doing the L'Hopital rule, or if you just use it even once more, then you will get a different result, which will be wrong. For example, if I use the L'Hopital rule on this part again, you can clearly imagine you just don't need to find the derivatives exactly. You can clearly see, since we have cosine functions, the derivatives will be some sine functions, that's for sure, right? We don't even need to find the exact derivatives. We can clearly imagine this, that if we find derivatives of this will be surely, doesn't matter the coefficients, this will be, or the signs, whether it's positive or negative, but it will be surely sine functions when you find the derivatives of these cosine functions, right? And we know that sine 0 is 0. So if we use the L'Hopital rule one more time, we'll have sine functions everywhere. And if we plug in zeros in place of the x's, we'll still have this indeterminate form. So whenever you have this defined value, you have to stop. You can't continue using L'Hopital rule. Does it make sense? Take your time, okay? You don't need to uh, just trust me and say, yeah, I understand, even if you don't understand, okay? If you don't understand, take your time, try to understand, and make me understand you again. Any question from this? From anything. It could be the algebra, it could be the reasoning behind it, it could be the trigonometric part, it could be the derivative itself. No questions at all? Okay, let me show one more example, and hopefully you might find a question. Okay, so let's see. Let's try. Excuse me. Okay, let's try this one. And then obviously I'll give you some problems to work with. So we have, let's say, limit x tends to -1, okay? And excuse me. And in the numerator we have 8x to the 4th plus 4x cubed plus 7x plus 3. And in the denominator, we have x plus 1. Okay, so that's the function, I think that's the limit we want to find, okay? Now, what's the first thing we need to do? What's the first thing we need to do? Anyone? What's the first thing you need to do when you are trying to find the limit like this?
Try plugging -1 into the x.
Very good. Yeah. First of all, we need to plug in this value, whatever we have, whatever x is approaching towards. So we need to plug that back into the place of the x's we have, or whatever the variable is, right? Obviously, if we have x here, we'll have x here as well. Or if we have t here, we'll have t here as well, whatever. So that shouldn't be a problem. So whatever we have, we need to plug that back into the place of the variable and check whether or not we have an indeterminate form. So let's see that. If we plug in -1, this will be, excuse me, this will be a +8, right? Because -1 to the power 4th will be positive, right? And so let me write it here. And this x cubed will give us a -1. So this will become -4. This x will give us a -1. So this will be -7. And obviously we have a +3 here. So overall it's -11, +11, which is 0. 0 in the numerator, right? We have a 0 in the numerator. Okay, let's check the denominator as well. So we have -1, +1, which is 0. So that means if we plug in -1 in place of the x's, we have 0/0, which is indeed the indeterminate form. Do you agree? That's the first thing you need to do, okay? At each step, we just need to plug it back into the place of the variable. At each step, we actually need to do that. Okay, since we have this indeterminate form, we can actually use the L'Hopital rule. Let's do that. Limit x tends to -1. What's the derivative of 8x to the 4th? This is actually easier than the previous problem, I believe. This is just power rule everywhere. It should be a straightforward one. What's the derivative? Yeah, go for it.
32x cubed.
32x cubed. The 8 will be here. For this x to the 4th, we'll have 4x cubed, right? Using the power rule. So that 4 times 8, it will be 32x cubed. So x to the 4th will give us 4x cubed, and we have an 8 in front, right? So it will be 8 times 4, which is 32x cubed, right? Let me use colors here so that you can see. Okay, what about the next one? Someone else? These are fairly easy derivatives, just using the power rule, right? What's the derivative of 4x cubed?
12x squared.
12 squared, using the same procedure, right? Oops. Using the same procedure, it will be 12x squared. What about the next one? 7x. Someone else?
7.
7. Okay. It will be 7. And of course, the derivative of 3. Anyone?
Zero.
0. Yeah, it's a constant. The derivative is 0. Okay, so the numerator is done. The denominator. the derivative of 1, obviously we know that it's probably the easiest of these terms, so it's 1, and the derivative of 1 is 0, so that's it. That's the derivative for us. So using the L'Hopital rule, you can say that this is equal to what we had initially. That means the derivative of this are equal to the main function when x tends to -1, right? Okay, what's the next thing we need to do? We have used the L'Hopital rule successfully. Now what's the next thing we need to do? I did give you a hint when I started this problem.
You need to plug -1 into it.
Exactly, we need to do it at each step, okay, after using the L'Hopital rule. That means we need to plug in -1 in place of x, in place of all the x's. So this x cubed will give us a -1, so it will be -32, right? This x squared will give us a +1, so it will be +12 plus 7. So we do have a defined value, and this is indeed our answer. We have to stop here. As I said, whenever we have a defined value, a value we can determine, we have to stop there. We can't use the L'Hopital rule anymore. Okay, if you use L'Hopital rule on this, then you will get a different result, and which will be wrong. Okay, so you need to know where you need to stop. It's really important to know this. Where do you need to stop? Okay, you can definitely use L'Hopital rule on this at least 3 more times, but it will definitely take you to some wrong result. Okay, so since we have a defined value, we need to stop using it and instead plug in the value we have in place of the variable. Any question from this? It was, as I said, it's actually easier than the example we started with, but anyway, that's how it is. Excuse me. Not every problem will require it using 3 times. Often, if you just use it even once, this will take you to your desired result. Any question from this? No question at all? Are you finding it doable? Are you finding it interesting? What's your opinion on this? Isn't it fun to work with? Because you can see it makes our life a lot easier, right? And obviously the derivatives are not that difficult to calculate either. We actually have dealt with much more sophisticated problems, derivatives, than this, right? All you need to do is to remember that if you have one of these indeterminate forms, just find the first derivative, replace it in its respective place, cross-check by plugging in the value again whether we have got rid of the indeterminate form. If we have, very good. Just find the value. If we haven't, keep using the L'Hopital rule unless and until we have this format. That means we have actually a value which is defined, which can be determined, right? Okay, so I'll give you a 5 minutes break. Meanwhile, obviously you can refresh yourself or you can cross-check this work. I'll have this open for you. If you have any question, just let me know, okay? Yeah, I have both the problems open for you. Just try to see if you can generate a question from it. And we'll meet after 5 minutes, okay? So first of all, let's consider this as e to the x, okay? I'm doing it separately, I'll replace it later. So let's consider this as e to the x. If it was e to the x, I would have written e to the x. The derivative would have been e to the x, right? But is it is it actually x? No, it's not x. It's something else. So that means using the chain rule, you just multiply the derivative of it. Do you agree? Do you agree? Okay, so the derivative of 18 over x, what's that? The derivative of 18 over x, obviously 18 is a constant, we can keep it outside, and the derivative of 1 over x, we know, is negative 1 over x squared. Do you agree? Take your time, okay? It was probably difficult, you know, especially when you have done so many easier calculations before that, before this particular problem. So it might be difficult. But again, if you use the chain rule properly, you can see it may not appear as difficult as it was when we started it, right? Okay, so finally you can write negative 18 times or negative 18x over x squared times e to the 18 over x. Do you agree with this? That's the first question. Is there any question on how did I get this? The derivative of e to the 18 over x is negative 18 over x squared e to the 18 over x. Hopefully I've done it right. Okay, how many of you have got this? Is there anyone at all? No one at all? Okay, no problem. No problem. We have already figured it out, so no worries. So now we can replace it here. So negative 18 over x squared e to the 18 over x. And let me keep it downwards, okay? And for the denominator, for 18 over x, we know the derivative would be 18 over x squared, right? So, did I do it right? Hopefully I have. Yeah, I think so. I think it's right. All right, so we can actually cancel this out and rewrite it as e to the 18 over x. Do you agree? Don't trust me, okay? Cross-check it. Don't trust me. Do you agree with this in the first place?
Yes.
Okay, thank you. So now again, obviously we need to plug in the value and check whether we have one of those indeterminate forms or not. And e to the 18 over infinity will be to the 0, which is 1. So that's our answer. Do you agree? does this actually make sense? Take your time, okay? Any question from this? Anything, even if it sounds really silly. No question at all? Okay. What about this one? So I don't think we have enough time to solve it, the third one, but I think that's easier of these three, right? This problem is probably easier than the other two. Anyway, so if we do that, let's see if we can solve it. So the first derivative of the numerator will be 2x minus 22, right? So it will be 2x minus 22. And what about the derivative of sine squared pi x? That could be a tricky one though. What's the derivative of sine squared pi x?
I had cosine squared pi x times pi.
Not really. I think that's wrong. Anyone else? All of you have the same result. So you can consider this as x squared. So it's 2x. I don't think we need to use the parentheses anyway. But if you want, you can keep it. So for x squared, we would have got 2x, but it's not exactly x. So we need to multiply by the derivative of sine pi x, okay? And it should be 2 sine pi x. The derivative of sine pi x would be cosine pi x and times a pi. Should write it below, yeah, times a pi using the chain rule, okay? The derivative of sine x is cosine x, but it's not really x, it's pi x. So you need to find the derivative of pi x and multiply it. And the derivative of pi x is pi. So it's actually 2 pi sine pi x cosine pi x. Any question from this part, this derivative? The rest should be pretty simple. And hopefully we'll solve it tomorrow if you want, okay? If you have a different derivative other than this, you can use this to recalculate the limit, okay? So let me know if you have figured it out. If you can't do it, I'll definitely solve it tomorrow, okay? All right, so your pre-class assignment would be to finish this third problem and to go over the slide antiderivatives 4.9. I'll see you tomorrow. Take care.